Hello and welcome to the first video of section 3.3 on how the first derivative affects the shape of a graph. The derivative of a function at a point is the instantaneous rate of change of the function. If the derivative is positive, we expect the function to increase at larger x values, while we expect the function to decrease after a point with a negative derivative. A function is increasing on an interval if we can choose any 2 points from that interval and the function is larger on the larger x value. Take the interval 0 to infinity. The function is increasing on the interval. The value 2 is less than 3, and f of 2 is less than f of 3. A function is decreasing on an interval if we can choose any 2 points from that interval and the function is smaller on the larger x value. The interval negative infinity to 0 is decreasing. The value negative 3 is less than negative 2, while f of negative 3 is greater than f of negative 2. We can use the first derivative to tell us if an interval is increasing or decreasing. If every point on an interval has a positive derivative, then the function is increasing on that interval. In the same way, if every point of an interval has a negative derivative, the function is decreasing on that interval. Take note of the wording of this test. It assumes that the function is differentiable on the interval. If a derivative does not exist, it can be neither positive nor negative. To prove that this test works, we will make use of the mean value theorem. F is defined on the interval x1, x2, and because this interval is inside of I, f is differentiable on the interval. Because f is differentiable on the interval, it is also continuous on the interval. Therefore, we can use the mean value theorem. On the interval x1, x2, we can find a value c which satisfies the mean value theorem. Manipulate the equation, move the denominator to the other side. Because x2 is greater than x1, x2 minus x1 is greater than 0. And because we're trying to prove part A, we're under the assumption that f prime of c is greater than 0. Because fx2 minus fx1 is equal to the product of two numbers greater than 0, it must also be greater than 0. And the inequality implies that f of x2 is greater than f of x1. This means that for any x1 and x2 in the interval I, with x1 being less than x2, f of x1 is less than f of x2. This means that the function f is increasing on the interval I. Following a nearly identical argument will lead you to the proof of B. Using the increasing-decreasing test, we can tell if an interval is increasing or decreasing. But how do we divide the real numbers into intervals on which f is increasing or decreasing? We'll divide the real numbers into subintervals using critical numbers, those numbers for which the derivative is 0 or does not exist. If the derivative of a function is continuous, by the intermediate value theorem, a value must exist which has a 0 derivative whenever the derivative changes from positive to negative or negative to positive. Take for example the polynomial 2x cubed plus 3x squared minus 36x. We begin by finding the critical numbers of the polynomial, taking the first derivative, and simplifying it. The derivative of this function is a polynomial, which is continuous everywhere. Therefore, by the intermediate value theorem, the only values where the derivative changes signs are the zeros of the polynomial, x equals 2 and x equals negative 3. We divide the real line into three intervals, negative infinity to negative 3, negative 3 to 2, and 2 to infinity. On each interval, the derivative is either always positive or always negative. Using test points, we find that the intervals negative infinity to negative 3 and 2 to infinity are increasing, while the interval negative 3 to 2 is decreasing. Notice that the graph supports the calculations and the theory. The first derivative can also help identify local minimum and maximum points. The first derivative test says that at a critical point, if the values to the left have a positive derivative, while the values to the right have a negative derivative, then the point is a local maximum. That is, to the left the function is increasing, but to the right the function is decreasing. At that point, you have a local maximum. In the same way, at a critical point, if the values to the left have a negative derivative, while the values to the right have a positive derivative, then the point is a local minimum. That is, to the left the function is decreasing, but to the right the function is increasing. Therefore, the point is a local minimum. If at a critical point the derivative does not change signs, then the point is not a local extrema. Going back to our previous example, we can apply the first derivative test to see that the x value -3 is a local maximum, while the x value 2 is a local minimum. To summarize, using the first derivative, we can find critical numbers, which we can use to partition the real numbers into intervals for which the function is increasing or decreasing. We can then use the first derivative test to determine which critical numbers are local extrema. In the second video for section 3.3, we will discuss how the second derivative affects the shape of the graph.